So this is based on joint work between Eddie and myself. We have both been concerned for some time with the issue of separate identification of probabilities and utilities when preferences are state dependent. I like to claim that efficient medical treatment comes from the combination of the probabilities of the doctors with the utilities of the patients. Now, clearly, medical treatment arises in many contexts where preferences are clearly state dependent. How you live if an operation is successful or not successful is very different. Yet the basic model of subjective expected utility maximization does not allow for state-dependent preferences. It is very easy to extend it to state-dependent preferences, but then you do not have separate identification of probabilities and utility scales because the probability multiplies a state-dependent utility, and if the two always come as a product, you do not identify them separately. I have been concerned with this question for 60 years, starting with my doctoral dissertation. Eddie is a newcomer. You have only 40 years on the subject or something like that. And I don't really know about you, but we contributed along parallel but separate lines. I was mostly concerned with moral hazard, meaning unobserved actions that affect the probabilities, whereas Eddie has been concerned with explicit actions affecting the probabilities, and importantly introduced observations as another source of information. Why actions and observations coming is easy to understand. If you are trying to isolate the impact of a probability and the impact of the event on utilities, and you want to separate these, you would like to observe choices involving the same utilities with different probabilities. How do you get different probabilities? By being in a framework where you have access to actions that influence the probabilities. And in the case of health, of course, there is plenty of evidence to that effect. Or you could make observations that modify the probabilities. And my purpose this morning is to present my view of how these two approaches complement each other for a very specific instance of observations. Eddie has been concerned with more general formulations. What I hope to show you is how these two sources complement each other and how this can be done in a technically quite elementary manner compared with the papers that both Eddie and I have published, which are certainly not elementary in terms of reading. We will start from a well-known paper. Now, if you start from a known paper you better make sure it's a good paper. And how do you know that? I think AAA is the best sign. And in this case, there is a AAA paper, Anscombe and Almond. So that will be, you know that paper, Bob, don't you? And you agree that it's AAA, Anscombe and Almond, right? But the framework of that paper will be extended to introduce actions which don't belong there, and in the second part, observations. The basic decision theory model relies on exogenous circumstances called states, on which you place bet by staking outcomes. The easiest is to think about outcomes as amounts of money. That's very simple, but they can be much more general and also can take the form of lotteries. When you include the actions, a decision will be a pair consisting of an action and a bet placing outcomes on the states. And in general, a consequence will be a triplet where you have an outcome, like an amount of money, the action which may have preference implications, and the state which again will have preference implications. Okay, do not hesitate to interrupt for clarification.
You don't have to say that here.
That was a clarification for me.
Sorry, the question? What does A do? What does A appear on?
Now, A is not part of the AAA model. A appears as an element of the decision. For instance, if you are concerned about a health problem, you may take an action like to have an operation or not to have the operation, and you may take an insurance which has implications in terms of the outcome.
What's the difference between a bet and
a bet?
that looks like an action.
A bet would be like the insurance company, which changes the consequences of whatever event obtains, whereas the action is a way of influencing the probabilities of the different events.
Oh, so I mean, something is missing here. At this point, A is completely abstract and does not interact with theta or with Z, right?
The model we want to use uses as primitives a set of states, a set of actions, given set from which choices could be made, a set of outcomes, and then a bet is a mapping from states to outcomes, and an action is an element of a given set. And the decision consists in choosing both an action and a bet.
Don't bet against one action. And what it excludes.
I don't know. At this point, A is not connected to anything, so I don't know. I guess in the next slide, it's to the utility function,
Well,
so something will happen. So something.
How is that different from states? You are given a set of states as part of the definition.
The outcome. The state, the bet, through the bet, the state determines the outcome Z. But the action at this point does not do anything. So I'll wait.
Okay. But you accept that I may give you a set of actions.
Yeah.
And in this case, you don't know how to choose one, but hopefully in a few minutes it will be better. no further questions on this, then the preferences are defined over decisions, the choice of an action and a bet. Again, let me use the example of having a medical problem for which you could go through surgery as one possible treatment, or you could go without surgery. There are implications through the state of health that may be very bad or better or whatnot, and that, of course, depends on uncontrolled elements as well as on the action that you take. You find it unnatural if
I don't understand action. How does action interact with state, consequence, something?
You have preference over decisions.
So I have preference
and action is one of them. And action is one of them.
Yeah, but it's not connected to anything. It's like a product. Okay.
The state is one of the components. The action that you take.
Okay. So it's like for each action I have a different model. Okay. For each.
All right. Very good. Very good. So.
Z and theta, and now you just put them together.
Very good. I will start with a single action. Then we are back to basically the Anscombe-Bauman-Savage framework, but with state-dependent preferences. And then when I introduce more actions, we will see that you are quite right in guessing this is like putting different models next to each other. And then, okay. So, no time to go into details. The beginning with a single action, you understand, is classical. So the preferences are over the bets, which are called acts in Anscombe-Bauman. They like A's all over the place. And you start with the so-called von Neumann-Morgenstern basic axioms: weak order, independence, continuity, non-trivialities is you have some choice. And then to go beyond von Neumann-Morgenstern, who use noun probabilities, you need two more axioms. In Anscombe-Bauman, the preferences are state independent, but we want to allow for state-dependent preferences. So what we want is that conditionally on any states, the preferences over outcomes be well defined. And that is one condition. And then there is one more condition called reversal of order, which has been a genuine contribution of the Anscombe-Bauman approach compared to what came before. Just think that you have two states: operation is successful, operation fails, and we talk about a bet where if heads you get 10,000 euros, if tails you get 2,000. Now this could be described in two ways. One way says the outcomes are determined by heads or tails after the state is observed. And the other approach is to say there are two bets, one which gives 10,000, the other which gives 2,000, and the toss of the coin decides ahead of the observations which of the two applies. The reversal of order assumption says in this model, where you do not do anything between the initial choice and the terminal realization, it doesn't matter that the bet be drawn before or after the states. That's reversal of order. And then with these assumptions, you get a formulation of expected subjective utility. We are keeping the action fixed, so you can forget about A. It is constant here, and it says a bet B is preferred or indifferent to B prime if the expected utility is higher in terms of some probability distribution. Where am I here? No. Yes. So, and as you see here, of course, clearly you could rescale probabilities and state-dependent utilities, and there is nothing in the model that can separate out alternative scalings. So the probabilities and utilities are jointly unique in the sense that the product is uniquely defined, but not separately identified. Okay?
What do you mean there is the family? What's the
family? If you have different actions, but you are not yet with different actions.
A is now a singleton, yes?
A is now a singleton. So. But now we introduce multiple actions. And the reason to do that is that with multiple actions, as we shall see, we can separate utilities from probabilities in favorable circumstances. The intuition is clear that if we have a way of influencing the probabilities, the way we do so will reveal which states are favorable and which are unfavorable, and we are on the way to identification. To do that, we must first of all assume that the conditional preferences are independent of the actions. Now one could deal with a more general model, but for today we deal with actions that do not modify the conditional preferences over outcomes. And now with several actions, we have a family of probability measures conditional on the actions. And this is essentially an extension of the single action case.
Sorry, I'll show my ignorance. When you had just one action, you said that the probabilities and utilities are not fully determined, only the product. But if you add the condition that sum of probabilities is 1, how can you rescale probabilities and utilities to get the same answer?
We can do it right here. You can multiply P of theta by some psi sub theta and divide u of b theta by psi of theta, so the product is unchanged, and then you have to rescale so that the new probabilities add up to 1, but that's just multiplication by a positive scalar. Makes no difference.
It's theta dependent in scale.
Right. Okay. Now let's see how we can go inside the information contained in the choice of actions. And this, I think, is the main contributions of Eddie and I getting together, and you will see why. Consider two actions, surgery, no surgery, two bets, amounts in euros, depending on theta, the state of health tomorrow, which may have 10, 20 different descriptions depending upon what happens, but we realize, of course, that they will be influenced by whether or not the operation was undertaken. Now I take a very simple case, 2 actions, 2 bets, and 2 lotteries. One lottery associates action A with bet B and action A prime with bet B prime. The other lottery mixes the other way. A prime B, A B prime. So A might be surgery, A prime no surgery. B might be full insurance, B prime might be limited insurance of the ensuing medical expenses. And then the lottery L will say, we will toss a coin. If heads, operation, full insurance. If tails, no operation, little insurance. That's a well-defined option. The other lottery says, if heads, no operation but full insurance. If tails, operation, no insurance. And the question now is, let's compare these 2 bets. That's
Lotteries, not bets.
when
What do you mean by full insurance?
theta is a number of possible values describing the evolution of your health tomorrow. And there will be, what?
What evolution? Evolution
Of your health.
my hand?
Your health. Whether you are healthy. Of course, you are so healthy, you do not worry
Only
about
one
that.
value
You
to that.
only one
The
value.
evolution
But-
of my health,
of-
yes.
Yes, and that may involve expenses, and these expenses may be insured or not. I want B to be some bet, and the interest of this condition is to force you to evaluate different mixtures between bets and actions. And the way that we do it is to consider lotteries where you modify the mixture between action and bets. Like to operate or not operate, with or without insurance. That's intuitive enough, right? And then if you are indifferent between these 2 lotteries, and you remember the theorem on representation in terms of expected utilities, then if you are indifferent, it must be that the expected difference in utilities between B and B prime is the same under A and under A prime. That's elementary algebra starting from the theorem. But now look at this. We have a vector of utility differences, and we take a weighted sum with conditional probabilities. Probabilities that are conditional on the actions. Now just imagine that we have a full set of different probabilities. If there are t states, we would need t different probabilities. Then we have here a full dimensional matrix, and if that matrix is non-singular, the vector of differences here must be constant. But that means we have identified the relative units of scale of the utilities in the different states. And the logic is elementary. It says we will know whether it is important for you, say, to have a longer life expectancy. How do we know it is important? Because you will insist on the operation if the operation is promising. That's how the choice of action reveals the utility differences across different states. Okay, I see a number of heads nodding. I see one.
Yeah. What prevents you here again multiplying all the pi's, taking pi, multiplying by some f of theta, and dividing u, comma theta by the same f of theta?
But we have several vectors here.
So independence of a. So that means a doesn't matter. That's what it says here.
What? Now,
What am I missing something?
if it is the case that these two lotteries are indifferent, then this value with an a here is equal
With a prime.
with a prime. And suppose there are only two states, theta and theta prime, then if p of theta given a and p of theta given a prime are different, this equality pins down this difference here as being equal
You
to
take all the pi's theta, or all thetas, and multiply by some f of theta, okay?
Okay.
And some function of theta, and take all the u's, comma theta, and divide by f of theta. I would still satisfy all the equations. Exactly, nothing will change. It was your argument from before, right? Just this is what you said. What prevents me from doing here? I do it for all thetas, for all a's, sorry. I do it for all a's.
but with the same f or with
The same f, the same f.
the same f, then of course you will have no way of rescaling the f so that the p theta add up to 1.
One for all a's.
You must for each a to add up to 1.
Okay.
Okay, you are with me? Very good.
So now I change the angle.
So how now could we identify the existence of a full set of linearly independent probabilities? And the way to do that is fairly simple. The conditions that we wanted to meet, you can always find bets that meet them, because there are conditions on utility differences between two bets, and you can adjust the bets so that you obtain utility differences that fit in the formula. How do you know that you have found a full set of linearly independent conditional probabilities? Well, it's fairly simple. If you have two B's that satisfy the condition, that is, for these two B's, you can reverse the association with the A's in my lottery. Suppose that taking one of the B's fixed and choosing one element from the other, choosing one element from the other says whether you will look for the other above or below the first one and by how much. If having fixed one bet and one element for a single theta from the other, there is a unique way of completing the other, that means that the relative units of scale are fully determined. No room to play with bets and keep the property that these lotteries are indifferent for all A's. So there is an operational way of identifying the property that units of scale of the state-dependent utilities are separately identified from the probabilities. Now, it remains true that this will give us a subjective expected utility result with separately identified probabilities and utilities, but we have done that under an assumption of action-independent utilities. The conditional preferences for given theta have been assumed independent of the actions. There is an open question that remains whether one could find conditions under which the action independence of conditional utilities is firm. But now I have only 15 minutes left, I understand. So I better move to the observations that will be faster and have some time. Okay. About observations, there is one example that my friend Eddie likes. He has a friend living in Florida, and a few years back there was a cyclone named Eddie that was raging across the Atlantic. So his friends called him and say, "Eddie, are you coming to Florida or are you headed for Tobago?" And that was an important question, because if you know that a cyclone is coming, if you knew it is coming to Florida, you might decide to go and spend the weekend in Chicago, or you might decide to close your house completely and bring some food to the basement and stay in the basement, etc. There are different strategies. So it is important to ascertain the probability that this cyclone is heading for Florida and not further south. Now, if you ask the meteorologists, they tell you tomorrow we will know almost for sure. Because no, because the cyclone is moving. We know where it is today, but tomorrow it will be much closer to shore, and whether it has moved north or south, it will still be probabilistic, but the probabilities tomorrow will be more reliable than today. So you ask the meteorologist, and could you tell us what you expect to happen by tomorrow? And he says, yes, on the basis of the situation today and our experience, there is 2 chances in 3 that we will find tomorrow a location threatening Florida, and 1 chance in 3 that we will find tomorrow a location threatening Trinidad. That's a clear example. So it means that tomorrow there will be an observation where the cyclone is tomorrow. And on the basis of that observation, there is still time to decide to go away for the weekend, close the house or whatnot. Now, the probabilities of the observation, well, better trust the meteorologist. What else could you do? So I am here, and this is not something that Eddie is fully endorsed. of course, he feels responsible for the cyclone and so on. But because I'm now going to model observations with known probabilities. The probabilities of the observation, not of the final outcome. I just borrow them from the meteorologist in this example. It could be from a medical research laboratory. It could be from the central bank. In some countries, in Greece, I know that I would rely on the probabilities of the central bank. But so this is an extension to observations of a statistical nature with given probabilities. And if the probabilities are given, it is very simple to construct a partition of the observations that are equiprobable. I told you a minute ago, probability heading for Florida 2/3, heading for Tobago 1/3. Is that what I said or the other? Yes. Now you could simply take observations of heading for Florida and obtaining heads in tossing a coin. Probability 1/3. Heading for Florida, tails in flipping a coin 1/3. So if you have a partition, which I label here E star I, into equiprobable observations, it is easy to find a counterpart to what I was doing with the association of bets and actions. Let us look at two bets, B and B prime. And now I will propose, starting from B prime, to replace it by B if and only if element I of my partition occurs. So for instance, B prime is little insurance, B is high insurance. If and only if the observation is I shift to high insurance, otherwise not. It might be insurance on the house that you own in Florida. If the observation says there is a risk of cyclone, I immediately take a higher insurance. That's the idea. And now we can look at pairs of bets. Everything we've been doing is pairs of bets, not single bets. Such that going from B prime to B, given one element of the equiprobable partition, is indifferent. Doesn't matter which one, right? And that means, in fact, that these bets, B prime, have again a property that the utility difference given theta weighted sum is independent, this time of I. Before I did not have I, but independence of A. The logic basically is the same. The source of information on the desirability of the different states is different. In one case, it was actions that influence the probabilities. In this case, it is information that is added and on which I can act. So again, you can detect operationally that you have found a B and a B prime for which the information is full. This we call strict. And we then have the results that with strict information, the probabilities and units of scale of state-dependent utilities in Theorem 1. Now we say are separately identified. We do not limit ourselves to action-independent preferences, because for the observations that would be irrelevant. And what is perhaps more important, second result, we can now identify the origins of the state-dependent utilities. How many minutes? 5 minutes. Very good. So I hope that I have shared with you the property that this problem of separating utilities and probabilities is susceptible of solutions coming either from actions that affect the probabilities of the events, or from information entailing implications for these probabilities and on which you can act. It is very important to my eyes that you can combine these two types of information, because typically they will bear on different aspects of reality. And of course, to have full identification, you need a very rich set of potential actions, or a very rich set of potential observations. When you put them together, you are capitalizing on information, on observation-dependent actions. So if you have n observations and m actions, there are nm possibilities from which you should retrieve t, the number of states, conditions on the probabilities and utilities. There remains more to be done in this domain. One would like to go from the states to events and work with events, because a full listing of states in most cases would be preposterous. And one would like possibly to extend the analysis to action-dependent preferences. Eddie has done some of that under another treatment of observations. The report essentially is, this is an area where some progress could be reported and more progress may be in sight.
Thank you very much. Questions? Time for one question.
Yes.
So in some sense, if you don't have this separation, or what I think that's what we call strictness, then I really don't care about the fact that I cannot distinguish, because for anything that is relevant, I get the same thing, even though I cannot separate the two. And if I can separate, it means that if it matters, then I should be able to separate. Is that a fair way to say?
I think there is a very general proposition in decision theory, which is somewhat elaborated in a paper by Aumann and Drees, 2000 something, that indeed you can identify parameters to the extent that they are relevant to decision. And in all cases where the separation of probabilities and utilities is immaterial, well, then you cannot infer them. very interesting exercise for you. You take the presentation of Bernard de Meyer this morning and ask yourself for all the parameters in his model, are they identified in observations of behavior or not? If you can answer that question by lunchtime, that will be good.
I'd like to add a comment. The answer also depends on the purpose. If you look at it from decision theory point of view, then you don't care about the separation, then I can tell you a more general model that applies to decision making regarding medical. So then you don't need the state independent produce it apparently for a purpose because you would like to have the representation of belief. But the more important is that when you think about the original work of Savage, it's called the foundation of belief. The idea there was derive a behavioral foundation for a prior. The prior have no meaning, and we are basically back to square one. Not identifiable with your basic value. So we don't have a theory of the prior. And actually, in this case, it makes sense to say instead of choosing a utility function which is state independent, choose the utility function that depends on the state, so the prior will always be uniform. Then you can start every Bayesian analysis from uniform prior. So the whole purpose of this exercise was to identify a meaningful prior representation.
Fine, thank you very much. You have 45 minutes. Thank you.
BBB, yeah, this one.
So go from AAA to BBB.
BBB, yes.
Let's talk with the system.
Okay, so first I would like to say that the choice of the topic was done for some reason. The first reason is that, in fact, the first time I talk about this topic was in Jerusalem in 1975. There was the second Belgo-Israeli conference, and we were in the Belgian house, and what is very nice is that many people who were there are here. Of course, the sad side was that Jean-François was part of the Belgian, and even Yossi is here. Jean-François was part of the Belgian group. There was Jacques Jaez also was there, and so I think it's a kind of souvenir to come back to this topic. Which also another reason is that it's somewhat related to some work of Jean-François on the ex-ante incentive compatible core, and I will say a word about it to show the relation. Although I have no new result about the core. Okay, so my purpose here is to take a very simple framework. The advantage of taking this very simple framework of direct mechanism designed with pure revelation, so no moral hazard, will be that everything will be elementary. So everything will be proved in some sense very simply, and so it will be very easy to. But on the way, this will survey some recent results which has been achieved, and especially result about individual rationality. And this is mostly the purpose of this talk, is to introduce individual rationality. Now, of course, typical applications in this area are the funding of a public good, or the reduction of a public bad, or the design of auctions. But there are new applications which I don't know very well, but some people are doing some work about computational mechanism design. And this is due to the fact that now with the internet, you can get a lot of information on individuals, because you have these cookies. You have these cookies in the and they as time goes on, they get a picture of you, of your taste, of what you think, and so on. So this is really a way to get a lot of data about individuals, and then you can design a mechanism which take into account all these information. That's all what I can say on this, but I think it's a new area of applications for this kind of mechanism. So the framework is very simple. We imagine a public decision involving n agents and a set of alternatives, capital X. Each agent has privately known characteristics, theta I, so we are back to the incomplete information model that Eric described. And we suppose that everything is finite. Now, to each type theta I, we associate a quasi-linear utility function. This UI depends on X and theta, but we will also examine, in some cases, they reduce this to the private value case, in which case UI depends only on theta I. Okay, so that's the private value. And then we have subjective probability distributions for each type on the types of and each individual I on the types of the others. Okay, and so this is really the given element in terms of the beliefs in the model. Now we assume consistency. Some result will not require consistency, but those on individual rationality will require consistency. So I assume consistency, and I assume that all the probabilities are strictly positive to simplify everything. What?
Why I just a constant for Claire I?
Why?
It doesn't depend even on its type.
No, yi is just to show that the utility is separable, but it will correspond to something in the model. So it's just a variable like that. It's just to indicate that this dimension is separable. Okay. Okay. Now we consider, as I said, we will consider direct mechanism, where the set of action of each agent is just a copy of theta I. So the idea is that an agent is asked to report his type, and then based on this report and the reports of the others, you have a public decision rules which chooses an alternative, and then we have this transfer which are given to the individual agents. Okay, this is the so there is a public decision rule and a transfer rule. Now, some very classical property. The public decision rule is called ex post efficient. If since we are in a transferable utility case, the sum of the utilities is maximized. Okay. And then we need also that transfer rule be budget balancing, and these two can do. So it means that the sum of the transfers should be equal to 0 for all state. And of course, if you combine these two properties, you get Pareto optimality. Okay, ex post, of course, here. Now. We can write the utility, the expected utility of an agent given a mechanism which I denote by UIST. Okay, and with this will depend both on the true theta I, so his true type, and since here actions are just to report types, the announced type theta I prime. Okay, and with the main property in terms of incentives is the idea of Bayesian incentive compatibility, and the mechanism is Bayesian incentive compatible if to report I permuted you have to put the inequality on the other side. Huh? If reporting the true state is give you a higher expected utility than lying, if you want. Okay, so this should be reversed. Okay. Now, as I said, what will be important here is to introduce also individual participation constraints, and there are two types of individual rationality that can be examined. One is the ex ante individual irrationality. We just say that the expected utility ex ante, so before each individual knows its type, should be above a certain level. These are the reservation utilities, U bar I, theta I, and they vary with I and theta I. And then a more interesting property is interim individual rationality, where the constraint is is written at the interim stage. So in terms of the conditional probability of individual I, so when he knows his type, and when at the time he has to report this type. Okay, two remarks about individual rationality. Of course, to imagine that you can get individual rationality, you have to assume that there is some kind of surplus that you can share. Because if you have no surplus, or the surplus is negative, then it will be difficult to get some individual rationality condition. And so this is a lemma that was proven by Matsushima in a JET article in 2007, that for any decision rule S, there exists a budget balancing transfer rule T satisfying interim individual rationality if and only if the expected surplus conditions hold. So it goes both ways. So of course, if you have an expected surplus, you can find balance transfer rules. This seems quite natural, but it also goes the other way. So that's a lemma that I will use later on. Now, a second remark is that ex ante individual rationality is easily derived. If you have a mechanism that satisfies Bayesian incentive compatibility and budget balance, you can always find design new transfers that will give you, in addition, ex ante individual rationality. And this is the construction that you can do. You just transform. So suppose you have U bar I is this level of utility, so this ex ante level of utility, U bar I, and what? I am summing over the
number of players.
Yeah, here, yes.
Yes, and on the right hand you have one player.
Ah, yes, you are right. This is also a mistake. Yes, this summation should be erased. Yes, correct. So this.
No. It's a total surplus.
Ah, yes, total surplus. Yes, this is just. No, I'm sorry. U bar I is just this element. Okay, the individual element.
You need a summation over I in the last.
Yes. Yes, here you need. Here you have a sum over I. Yes, correct. Now, so you can just transform the transfers in this way, and then you get exactly that every individual will reach the level Vi. Okay, so that's the. So in other words, you can always, by such a transformation, get individual rationality. Example. This is not a new result. I mean, this is a very standard observation, but it's. So let me give the starting example. This starting example, I call it the starting example because it was the example given in 1975, and it's so it is very easy because it's a generalization of the Vickers-Clark-Groves-Metz mechanism, but in expectation. So so you assume that the probabilities are independent, or what is sometimes called freeness. Okay, so in other words, that the conditional probability is the same for every theta I. And we assume also private values. So this is a very simple case where we have independent probabilities and private values, and we take the public decision rule to be efficient. Okay, so these are the three main ingredients. Then you can define the transfer in the following way. Here you have the expectations of the utilities of the others for each individual I. Okay. So in that sense, this is really the Groves part, but in expected value. And then you have an additional term which is just to balance that you introduce just to balance the budget. Okay, and then you get that this with this scheme, so S star and these transfers, you get efficiency and budget balance and Bayesian incentive compatibility. So this is just a reminder, and of course after that there was some kind of extension that were made in the sense that the idea was to keep the assumption on the utility separability, but to see whether you can increase the class of probabilities or distribute of subjective probabilities for which beliefs for which this positive result still holds. And in fact, it appears finally that there are a very, very large class of probabilities for which such a result holds. Thank you. So here I just list a certain number of them. Okay. The most recent one with Koznock and Severinov in 2008. I will concentrate on this condition, condition C, which was called the compatibility condition. And this is because it is very simple to handle, and but it is equivalent to a condition which is given in Johnson, Pratt, and Zeckhauser, which is called link, and weak identifiability of Koznock and Severinov. Okay, so these are, but of course, each of these conditions may give you some additional results because they are stronger, so you can get additional results with some of these conditions. Now, so this is condition C. Condition C is a generalization of the previous condition in independence, but it's much larger than independence, and it just says that for any budget that you want to reach, there exists a transfer rule, which I call TC, such that you can get this budget, okay? And this transfer rule is incentive compatible. So in expectation, you are, it's like if you have the utilities identically zero, if you want. So for utility identically zero, you would be encouraged to tell the truth, okay? Just in terms of the transfer that you are receiving.
That's a condition on the probabilities PI.
And this is the only condition on the probability PI. Yes, the only thing which appears here are these probabilities. So it's a condition on the probabilities. Now, you see this is a system of linear inequalities. So you can always reformulate this condition in terms of dual conditions. And so in this literature, alternatively, some people work with the dual or work with the primal. So it's really a matter of convenience. But this is, of course, very transparent because it just says that if your utilities were identically zero, you would be encouraged to tell the truth just by receiving this payment. Okay, now, here I use the term used by Jean-François Mertens, automatic balance. So for any Bayesian incentive compatible mechanism, ST, there exists another Bayesian incentive compatible mechanism, ST prime, with budget balance T prime, if and only if condition C holds. So in some sense, conditions, the generality of condition C is that condition C ensure or guarantees budget balance. Okay. This is not to say that condition C is a necessary and sufficient condition to get the result we had with independent, but it's the most general condition if you want to reach balancedness. Okay. And the proof is very easy in one direction.
That's a question. What happens when the dependent case?
The condition C holds include independence.
So P does not depend on theta I.
Yeah, then condition C
automatically
holds, yes. And it holds even if you have one individual who has independent probabilities, it also holds. So you have a lot of cases where, but what is important, and I think, is that C is compatible with independence, and that's important. So the proof is very easy because you use the budget that you use the budget that you have to balance the budget, and then of course you get the. So if you take a big mechanism, you change the transfer thanks to condition C, you add the two types of the two transfers and you get the result. For the other direction, you have to construct a utility function and you make these utility functions such that the two cancel, so you don't have incentives problem. And then you show that that there exists another big mechanism satisfying budget balance, and so condition C is satisfied for this when you add the utilities and the transfer, and this is just that. So it's just going back and forth. Okay. Now, the main one application is that with condition C. With condition C, you get the first best. So you can implement the first best, okay. And of course, by the trick I mentioned before, you can always ensure ex ante individual rationality. And so this is just the idea is to take the Vickers-Clark-Groves transfer rule. So this is a Bayesian, it's incentive compatible in dominant strategy, but so it's also incentive compatible in Bayesian. And then you use the preceding lemma and you get what you want. Now, another application is to consider the exchange economy with L goods that is considered in the article by François Forge, Jean-François Mertens, and Rajiv Bois in Econometrica 2002. So you define for the utilities, you define the endowments, which might depend on the types, and then you define the set of feasible allocation for each coalition, and the mechanism is a public decision rule for the coalition and transfers, and you ask that the transfer be less than or equal to 0. So there is a condition on the transfers. Now we can define the two following characteristic function. in ex-ante payoff. This is the one, the most classical one, where you just you make the sum of the utilities, okay, of the ex-ante utilities, and then but then you have another characteristic function where you make the same sum, but you impose Bayesian incentive compatibility. So this is so you have a VS which is of course smaller because you you have to respect the constraint of Bayesian incentive compatibility, and the idea is to study the core of this new game where you have these incentive compatible constraints. Now, under standard assumption, the core of the usual game is different, is non-empty, and then on the application, this is just to mention the application under condition C, the incentive compatible core is also non-empty, and this is very easy to see because of condition C, V star n. First of all, ex-ante efficiency, because I assume that all the probabilities were strictly positive, ex-ante efficiencies coincide with ex-post efficiency. Now, because of V star n is equal to Vn, because of the condition C, we get that the core is non-empty. So that's a very straightforward application. Now I should say that in the article they do much more than this. They introduce stochastic public decision rules. They see what happens without condition C, and they exhibit an example for well-behaved exchange economy in which the ex-ante core is empty. But this is outside the private value case and with one fully informed agent, so we are outside the application of condition C. Yes?
So if you have independence, then condition C will probably be satisfied also by the subset.
If what?
If you have independence,
yes,
the PI,
yes,
then condition C will also be satisfied for every subset.
Yes.
Which means then that V star and V are exactly the same.
Yes,
game.
exactly. Yes, yes.
Okay.
Okay, now, so the idea now is to, so these are just known results, and so I will, but now what about participation constraints? Here we have, of course, a lot of results which were derived for the independent beliefs case. So most people at the start would look at the case where maybe thinking that it was the most easy case, but in fact it will turn out that it's the most difficult case to impose independent beliefs. Now, what we will consider is the correlated case, so the non-independent case, and there are some recent article by Matsushima in JET 2005 and Koznock-Severinov in JET 2008, which do exactly that. And so I will mention their result later. So what is interesting is, and this is what is nice, is that in fact we can just modify condition C in a very straightforward way, and we get a positive result with interim individual rationality. So the idea is the following: instead of having only a budget, okay, you introduce a budget and individual requirements, Ri, theta I, and so you impose the following conditions for any R and any vector of Ri that satisfy this expected surplus condition. Okay, and so for all R and all Ri, you need budget balance. You have the Bayesian incentive compatibility, and in addition, you have interim individual rationality with respect to the Ri. Okay, again, this is only a condition on the probabilities. It's only a condition on the probabilities, but then you can then you can prove that these two statements, that condition C are holds, so the new condition C holds, if and only if for any utility function and decision rule S satisfying the expected surplus assumption and such that ST is a Bayesian incentive compatible and individually rational, there exists a budget balance transfer rule such that ST is also a big mechanism satisfying IRS. So you, in some sense, you again obtain what was called automatic balance. So CIR is necessary and sufficient to balance any Bayesian incentive compatible mechanism which would also satisfy, thank you, which would also satisfy individual rationality. So the proof is very, I put the proof, I don't think we will go through the proof, but the proof is really very, very simple. You have to define, from one direction, you have to define R, the big R, okay, and you just take the same idea that big R will balance the surplus. The only new thing is that now you have to define the Ri, you have to define the small Ri, and of course by the expected surplus assumption, the sum of the expected value of big R is greater than or equal to the sum of the small r, okay? So you get what you want here. Since we also get, because of the condition, we also get Bayesian incentive compatibility. So the only last thing to verify is that you have individual rationality, and this is like the construction of the Ri. You get this inequality, and so you get individual rationality. And of course, you can prove, it's a little more difficult than the previous case, but you can also prove that 2 implies 1, that if any utility function, you can do that, you have, you can derive condition C, so you have to get the reverse condition. Now, again, also, so all these are the repetition, or in some sense, of the previous result, but now with individual rationality and the modified condition C. So the argument are very, very similar. So you can also get, if you have efficiency, you can also get a budget balancing transfer rule, which is Bayesian incentive compatible and satisfies individual rationality. So this result here is the proof is the same. In fact, you start with a Vickers-Clark-Groves mechanism. You increase the transfer by any constant so that you get individual rationality, and then you apply the condition and the lemma, okay? And then you balance the budget because of condition C. Alors, what is important is that in contrast with the original condition C, here independence or freeness is not included. And in fact, we have a condition which we can call no freeness, meaning that no agent has free beliefs over 2 types. Okay, so for all I and different types of Mr. I, the probability distribution should be different. Okay, this is a condition which is quite known. This is called belief announcement in Johnson, Pratt, and Zeckhauser, and it's called belief determined preferences in Aviad paper. So this is a condition, but this condition is necessary if it. Yes.
Is there a way? So the condition C and CIR say for every R something.
Yeah. Yes. Yeah.
Is there a way to translate into finite many inequalities when you go to the dual somehow? Or
you can go to the dual. Yes.
No, but it's finitely many inequalities or infinite.
No, finitely many.
A system of inequalities of that kind.
Everything is finite here. The number of types is finite. Everything.
That doesn't, because the condition C at its state that it says for any function now, which means for any vector.
For any.
So
yeah.
those are infinitely many conditions.
No,
so the question is whether you go to the dual or something. This translates to finite.
This translates to finitely many conditions. Yes. Yeah. Absolutely. Now, this lemma just says that C proved the fact that CIR implies no freeness. So in that sense, you have when you impose the new condition C, you have no independence at all. Okay, you have you exclude independence. Yeah, so that's a very strong conclusion. I mean, a strong implication of this condition. The proof is quite easy because, in fact, you see that if the two, since by individual rationality, you have that at least that one is. You have one of these should be bigger. You take Ri so that one is bigger than the other, okay? And if you take capital R so that this is equal, okay? If you take big R so that this is equal, you get a contradiction because you get that the sum of the T are bigger because of the individual rationality condition. You get that the sum of the T are bigger than R, which should not be because it should be equal. So you get a contradiction very easily. So let's we are going to introduce another condition. This condition could have been defined also without individual rationality. I didn't define it just for short, but and this condition was used also in the Mertens in the Forge-Mertens-Bora paper, but without the IIR. Okay, without the IIR. And the difference is this equality here. So the idea is that there exists a balance transfer rule such that for all I and all theta I, there is a Bayesian incentive compatibility with respect to these transfers. And in addition, this is zero. The sum of these, the expected here is zero. So in some sense, this is zero and this is negative if you want, okay? Now, for any decision rule satisfying the expected surplus condition and belief satisfying this condition, there exists a budget balancing transfer rule T such that ST is a Bayesian incentive compatible mechanism satisfying individual rationality. Now, I should say that this condition is related to the condition used by Matsushima and used by Koznock and Severinov, in the sense that Matsushima, both conditions being inspired by the condition of identifiability introduced by Fudenberg, Levin, and Maskin, first in an econometric article in the Moral Hazard and Repeated Game Framework, and then in a discussion paper. Is it published now, this? Okay. And then so the condition used by Matsushima are stronger, and the condition used by Koznock-Severinov is equivalent. In fact, it's Koznock and Severinov use a condition which is a combination of identifiability and of Kremer-MacLean condition. So it's a mix. It combines the two aspects. But so the result I will state are the same. The proof, of course, here is very simple because what you do is you use a big M argument in the sense that if you you can always, by Matsushima lemma, find the budget balancing transfer rule. Mm-hmm. So participation holds, okay, because of we have assumed that we have the expected surplus assumption. And then you construct tau plus M times t b, and of course taking m sufficiently large will erase all the counter incentives, so you get incentive compatibility because you can take m very large. And because of the second condition of B, it will not affect participation, okay? Because you have this is equal to 0, multiplied by m, big M, it's also equal to 0, so you don't affect participation, okay? Now, another remark is that condition BR implies condition CR. Now, let me just mention an important fact is that this condition, because of this big M argument, you will not. We don't require private value, so we can have common value here. We can introduce common value, which is, of course, something important. And the last thing I want to do is to prove that these conditions are non-empty, because when we had the initial condition C, we knew it was non-empty because it included independence. So, in fact, we can show that this is, in fact, these conditions are generic. But to show that this is not empty, I give a constructive argument. Okay, and the constructive argument consists, you know, in the statistical literature. Just before, with subjective probability, they had some problem of how to devise means to elicit the subjective probabilities. And the idea was to pay someone a certain amount so that he will reveal his subjective probability. And the idea was that if you pay to someone the logarithm of his probability, he will tell the true probability. So this is something which is used here, but of course here we have, in addition, that there are several people that should reveal their probability, and that we have also the budget balance condition. So that's why this is an idea in Johnson, Pratt, and Zachauser. We organize we order the agents in a circular way, okay, and so we index the agents modulo n. And then we define these probabilities. This is just an example, because there are other types of proper scoring rule. But we suppose that this is strictly positive. Okay, this marginal over for theta j, and then we construct this transfer scoring rule. So which involve as you see, the logarithm of the probabilities, okay? But we go, the trick here is to go both ways. We go on one round on one direction, and then we go in round in the other direction. Okay, so it goes both ways, and then we have these variables in addition, and these variables should satisfy. Oops, I'm going too quickly there. This variable should satisfy the condition, the second condition of condition B, which is this set of equalities, that it should be equal to 0. But we have 2 times theta I variables, so we have a system of 2 times theta I variables and theta I equations. So hopefully, by moving a little the probability, we can find a solution. So we then solve this system in the GIs, okay? And once we have solved the system in the GIs, we have this condition which is satisfied. So the last thing is to show that this is budget balance. No, it's not the last thing. First, you have to show that this is budget balance. This is just budget balance by construction, okay? We made things such that it balances, okay? And then the last thing is to show that it is Bayesian incentive compatible. And this is done by, so we eliminate the terms that are constant in theta I. So this is the logarithm of the difference between the logarithm pi minus the logarithm when he says, he's announced theta I hat, and here when he announced the true theta I, okay, let's say. So this is for the first term, it's the second term. And so this, we have to show that this difference is negative, okay? So with just sum over the theta, which are not theta I plus 1, we get this term. Then we have, by Janssen inequality, we have that the sum of the logarithm is strictly smaller than the logarithm of the sum, okay, if these terms satisfy a certain strict inequality. And each of these terms is equal to 0 because we take this cancel this cancel with that, and this sum is equal to 1. So we have 2 times the logarithm of 1, and so we get 0. So by construction again, we get that this is Bayesian incentive compatible, but of course, so for the inequality to be strict, we need this difference to be verified. Okay. Okay, so that's the end, and so we know that now this argument indicates, because by moving the prior probabilities a little, you can always get the conditions that I mentioned. But in fact, there are other arguments to show. It's very important to know that we need n greater than or equal to 3. So in the case n equal 2, it doesn't work. This condition is empty for n equal 2. So we need n greater than or equal to 3, and these conditions, genericity is also mentioned by Matsushima for his conditions, and also by Koznock and Severino for their conditions, which are, this is equivalent. So this is. Now I should mention that in any case, in all those cases, we have to require no freeness. Okay, we have to require no freeness, and there is a paper by Heifetz and Neyman that in the infinite case, this may cause problem. Okay, in the infinite case, this may cause problem, but in the sense that this condition is quite important. So what are the conclusions? Well, the conclusion is that the conditions on belief are helpful not only to implement the first bet, but also the ex-ante incentive compatible core. And of course, there it would be nice to see whether we can use the new conditions, C, I, R, and the B condition to get additional results on the core, for some kind of interim core. The one important thing that was mentioned by Geoffroy Klippel is that in the paper by Koznoff and Severinov, they show that with condition B, you can get any kind of redistribution of the surplus. So in some sense, it would indicate that there is something that you could define side payment games with interim inutilities, but this is to be checked, of course. So here, the reason why we go beyond the impossibility result of Roger and Meyerson and Satterthwaite is that we have more than 2 agents and no freeness. Okay. Now there's still an open question. We have seen that we have in one side we have condition C, and we have condition B. Condition B works very well. Very simple argument, the big M argument, and work for the common value case. Whereas condition C does not work for the common value case. It works only for the private value case. So there is still one possibility. So the idea is, can we avoid no freeness, because we didn't go at the limit in some sense in the C with the C conditions. It's not a necessary and sufficient condition to get It's just a necessary and sufficient conditions to balance the budget, but it's not a necessary and sufficient to get all the properties. And so we could go further, maybe, with condition C in the private value case, and get maybe something maybe a little bit of independence. I don't know. I don't know. So that's the open question. Thank you very much.
There is lunch now. There is an urgent question. You can ask it now. But you can ask him over.
Or at lunchtime. Yes.
The CIAR sounds somehow like a dimension condition, but it's something's full dimension.
Yes.
Whereas the